Now, the concept we're talking about in this video is to do with index equations. This is the key idea you need to keep in mind. If you've got a to the power of m being equal to a to the power of n, then m must equal n. Because if this power is exactly the same as that power, that base is exactly the same as that base, that index must be exactly the same as that index. So let's have a look at a couple of problems. Now, 3 to the x plus 1 is equal to 81. In these type of ones, you should be trying to look at the base and see if you can turn the base into the same value. Well, 3 is base 3, so that's nice and easy. We're just going to leave it as that. But 81, I know that is 3 to the power of 4. If you don't know that 81 is 3 to the power of 4, just guess that it might be a power of 3 and just use your calculator and keep timesing by 3 until you reach 81, and you'll soon find out that 81 is 3 to the 4. So using this concept that a to the m is a to the n, therefore the indices must be equal. Powers are equal, bases are equal, therefore the indices must be equal. So our unknown value must be 3. So if I put 3 back up into here, I'll get the right answer. 3 plus 1 is 4, 3 to the 4 is 81. Great, everything is fine. Now, in this case, it's a little bit more complicated with the indices, but let's see where it leads. Now, when I look at this, I can see clearly that 36 is 6 squared. So that'll be my common base. So 6 to the power of 3x minus 1 stays the same. Now, this bracket here, the 36, I'm going to write it as 6 squared. I like the idea of keeping this base number inside the bracket, very useful. The index, 2x minus 3 stays the same. Now, using your power to a power law, the inside power, 6 squared, is raised to the 2x minus 3. So these two indices have to multiply together. So it's going to be 6 to the power of 4x minus, be careful, if you're going to make a blunder, here's where you're going to do it. You times all of this by the 2. So 2 lots of 2x is 4x, 2 lots of minus 3 is minus 6. So therefore, indices must be equal. So therefore, it's 1 lot of x on the right, that's going to be 5 on the left. Our unknown value must be 5. On this one, I've got 2, 16 and 32 are my base numbers. I recognise them all as being powers of 2. So 2 to the 3n will just stay as 2 to the 3n. Take my 16 out and make it 2 to the power of 4 in a bracket, all raised to the n plus 1. 32 is going to be 2 to the power of 5. Now, do my power to a power law. That remains unchanged for now. That's going to be 2 to the power of 4n plus 4. So I'm multiplying now powers of the same base, I add their indices. 3n plus 4n is 7n, plus the 4. Go back to my original concept, I have powers that are equal, indices must be equal. So 7n plus 4 must be equal to 5. Take the 4 to the other side, so that's going to be 1. 7n is equal to 1, n must be equal to 1/7. Okay, one more example to go. I'll clean the board off and I'll come back and show you. Okay, here is our last example for today. Number 4. This is actually what I call a quadratic in disguise. Let me just have a look at this 5 to the power of 2x for a moment. I'll bring it over here. So that's 2 multiplied by x. You remember your power to a power law? So if I've got one power inside to a power outside, I times the indices. Well, here the indices times together. So if I wanted to, I could write it as 5 squared power of x. No reason why I can't also write it as 5 to the x to the power of 2. Either way, it's still power to a power. Here, I could times the indices to get 2x. Here I would times the indices to get 2x. So can you see that I can rewrite this in that format? If you can, that's the essence of the question right there. So I'm going to take 5 to the power of 2x out. I'm going to rewrite it as 5 to the power of x squared, and then the rest of the question stays the same. Can you see the quadratic in here now? Something squared minus 4 lots of the something, take away 5. So here's like your something squared, it's out of the term, and then your constant. It's a quadratic. So what I'm going to do, it's a bit of a complicated quadratic, so I'm going to make it a little more simple for the time being. I'm going to, this bracket bit, the 5 to the power of x, I'm going to take that out and let that be equal to a. Any pronumeral you want. So long as you don't make it equal to x, make it equal to any pronumeral you want. So I can now rewrite this as a squared minus 4 lots of a minus 5 is equal to 0. A very easy quadratic to solve. That factorizes easily. That's going to be a minus 5, a plus 1. So therefore a is equal to 5, or a is equal to negative 1. Beautiful. I've solved this quadratic quite easily. I just haven't solved this one up here yet. So I took this complicated thing out and I put simple a in. So now I can take simple a out and put the more complicated thing back in. So if a is equal to 5, therefore 5 to the power of x is also equal to 5. Or 5 to the power of 1 if you like. Therefore, the unknown value must be 1. But mind you, I can take this a out and put 5 to the power of x in, is equal to negative 1. Because we know our indice graphs, there's no possible way that 5 to the power of x can be made to produce an answer of negative 1, so therefore no solution. So, there is our one and only solution to our original problem. Alright, so good luck with them. Now, give me a moment, I'm going to clear the board off a bit more and give you some entry card questions to get into class. Now, just to help demonstrate your knowledge of the stuff that you've just seen on the video, when you turn up to class, I want you to show me these 3 questions completed. These are called your entry card questions. If you can get them out, they're all based upon the video. Get them out, you're going great, that's awesome. Now if you can't get them out, don't sweat, don't panic. Just show me your attempt, show me what you've done, and that'll form the basis of how we're going to start next lesson. So, as well as your notes from the video that you've just watched, these 3 solutions fully done. And I'll see you in class and I'll check how that's going.